You ever just look at something and wonder how it gets so perfectly smooth? I mean, think about the glass on your phone or the paint on a brand new car. We're just surrounded by these flawless surfaces, right? Well, that perfection, it's not as simple as it looks. In fact, it's the result of a hidden, high-stakes war that's being fought at a microscopic level every single day. So here's a fun one for you. What in the world does your phone have in common with a massive 500-foot ship? I mean, really think about it. One fits in your pocket, the other hauls thousands of tons of stuff across entire oceans. They're like the complete opposite of each other, right? Well, the answer is their skin. Seriously, both of them totally depend on these incredibly advanced, often invisible coatings just to survive. And let me tell you, the science behind that protective layer, it's absolutely fascinating. And that brings us to our first big idea here. The surfaces we see and touch every single day, they're actually pretty deceiving. We look at them and we see simplicity, but underneath all that, there's a whole world of intense scientific and engineering effort going on. Just let this quote sink in for a second. That perfect finish on a product, that flawless gleam, it's not just some final step in the manufacturing process. No way. It's a victory. It's a hard-won fight against a relentless army of tiny, microscopic enemies. So, who are the bad guys in this story? Well, we're about to dive right into the battle against imperfection. And this is a battle where even the tiniest, most insignificant-seeming flaw can lead to a total, catastrophic failure. Okay, let's meet the lineup of microscopic villains. You've got things like bubbling, which creates these ugly little fisheyes in paint. You've got tiny cracks that can literally shatter a sand mold. And then there's the slow, creeping death of corrosion that just eats away at metal. Every single one of these is a huge threat. To really get a feel for the scale of this fight, let's just zoom in on one of these guys, the humble bubble. We're talking about a simple air bubble in a coat of paint. Seems pretty harmless, doesn't it? Yeah? Think again. So check this out. Researchers found something really fascinating about this. When you're dealing with a spray coating, the really tiny bubbles, they actually shrink and just disappear, all on their own. But the bigger bubbles? Oh, they stick around. They grow as the paint dries, and they create these pits that completely ruin the surface. So the size of that one bubble, it literally determines the fate of the entire finish. Crazy, right? And look, this isn't just about a drop of paint. The same kind of battle is happening everywhere. In digital casting, trying to mill a sand mold can make the whole thing crack and collapse. In a steel mill, tiny impurities can weaken a ton of steel. These microscopic enemies, they are everywhere. And the consequences, if you ignore them, they're massive. So the big question is, how do you fight an enemy you can barely even see? Well, you start by making it visible. And that's what we're going to talk about now, how scientists are basically building digital worlds, digital replicas of the real thing to predict and defeat these tiny threats before they even have a chance to form. The key weapon in this fight is something called numerical modeling. Okay, the best way to wrap your head around this is to think of it like a flight simulator. But instead of a jumbo jet, you're modeling the behavior of molecules in molten steel or the flow of paint coming out of a spray gun. It lets you test all kinds of crazy scenarios on a computer, which is great because you don't end up blowing anything up for real. And the process itself is super methodical, but also really powerful. So first, you lay down the ground rules, the laws of physics that control the material. Then you build a digital twin, an exact replica of the whole process. And then the fun part starts. You get to play with everything. Tweak the temperature, change the speed, up the pressure. You can change every variable you can think of and just see what happens. And at the end, what you have is a solid prediction of how it's all going to play out in the real world. Okay, I know that might sound a little abstract, so let's make it super concrete. Let's head over to a steel mill. In steel mills, they use this protective coating called slag when they're casting the steel. It's really important for making sure the final product is high quality. So, using this kind of modeling, researchers found something they totally did not expect. When they cranked up the casting speed, the amount of that protective slag they used per area actually went down a little bit. But, and this is the key part, the slag used per length of steel, it shot up by almost 27%. Now, that is a critical piece of information you would never figure out just by trial and error, and it helps them make stronger steel way more efficiently. In this power of prediction,
It's being used all over the place. We're talking from the steel mill example we just looked at, to using AI to predict exactly how fast a metal is going to corrode, all the way to simulating the insane heat of a plasma torch to make sure it doesn't melt the stuff underneath. Being able to see the unseeable, it's a total game changer. But listen, digital predictions are only half the battle. That's great, but you still need the actual physical tools to go out and create that perfect surface in the real world. And that's where some really cool new inventions come into play. Okay, let's jump back to that problem with digital casting for a minute. Remember, you've got these huge molds made out of sand, but they're super, super fragile. So when you try to shape them with normal tools, they just crack, they crumble, they collapse. It's a massive headache for manufacturers. So what's the solution? It's pretty incredible, actually. Ultrasonic milling. Instead of just using brute force, this technique uses a tool that vibrates more than 25,000 times a second. It just gently and super precisely chips away at the sand. And the results? They are absolutely stunning. This method reduces the cutting force by almost 20%. So what does that mean? It means way less stress on the mold, which means fewer defects, and a much, much higher quality final product. It's a complete game changer for them. And this type of hands-on innovation is happening across all kinds of industries. To paint those enormous ships evenly, engineers are building these amazing variable flow robotic sprayers. To protect furnaces from super high temps, they're using something called cold spraying with titanium dioxide to create a shield against corrosive gas. And to make even stronger materials, they're now combining plasma spraying with lasers. It's like every single problem demands its own unique and brilliant solution. So where does all this leave us? Well, it kind of shows that the future of technology, in so many ways, is literally skin deep. Some of the biggest and most important breakthroughs are happening at a level that we can't even see with our own eyes. Here's the really crucial thing to take away from all this. Our entire modern world, everything from the phone you're holding to the power plants that keep the lights on, it all runs on surfaces. And these surfaces, they aren't just passive things. They're active, highly engineered battlegrounds. They've been designed with incredible precision to win that invisible war against friction, heat, and decay. And that just leaves us with one final thought to chew on. As our technology keeps pushing the boundaries, getting smaller, faster, hotter, and more extreme in every way, the demands we put on these surfaces are only going to get crazier. So the real question is, what invisible coatings, what impossibly perfect surfaces are we going to need to invent next to build the world of tomorrow?